There are machines that make noise, and then there are machines that make silence impossible. On a winter morning during the height of World War II, inside one of the largest industrial complexes ever built in the United States, a sound began forming deep inside steel. At first, it was barely noticeable. Factories are never quiet places. Steel presses slam, conveyors rattle, furnaces roar like contained storms. Workers shout instructions over the constant vibration of heavy equipment. Against that background, small changes are easy to miss. What began that morning was not a bang or a sudden crash. It was a change in rhythm. Deep within a massive rolling machine used to shape armor plate, the rotation of steel cylinders developed a vibration that did not belong there. Not loud, not dramatic, just different. Most workers never noticed it. Those who did assumed it was temporary. Industrial machines often produce strange sounds that disappear as quickly as they appear. But inside the rotating mass of hardened steel, something had already begun moving toward a point where it could no longer remain contained. It was not an explosion waiting to happen. It was something more predictable. Physics reaching a limit. And within moments, the environment around that machine, workers, equipment, concrete floors, and the production lines feeding armored vehicles into a global war would be forced into a sudden and violent interruption. No alarm sounded. No countdown began, because the machine had already crossed the boundary where warnings matter. To understand the moment when the machine failed, it helps to understand the world that created it. By 1942, the United States had entered World War II with an industrial challenge unlike anything it had faced before. Modern war required enormous quantities of equipment, ships, aircraft, artillery, and perhaps most urgently, tanks. Armored vehicles had become central to modern combat strategy. Battles across Europe and North Africa demonstrated that mobility combined with protection could determine the outcome of entire campaigns. But tanks were not simple machines. Each one required enormous quantities of specialized steel. Armor plate had to be thick enough to resist high-velocity shells while still remaining workable enough to shape into complex hull structures. Producing that material demanded large industrial systems capable of shaping steel under extreme conditions. In response, American industry began building manufacturing facilities at unprecedented speed. Entire factories appeared where farmland had existed only months before. The Detroit region became one of the most important centers of wartime production. Automobile companies that once produced passenger vehicles rapidly converted their engineering expertise towards military manufacturing. Assembly lines originally designed for cars were redesigned for tanks. New facilities were constructed to support every stage of production, from steel processing to final vehicle assembly. These were not small workshops. They were industrial landscapes. Buildings stretched hundreds of meters. Rail lines ran directly into factories to deliver raw materials. Inside, machines operated around the clock under rotating shifts of workers who kept the system moving 24 hours a day. Speed mattered, volume mattered, because every week of production delay could influence battlefields thousands of miles away. And within this enormous system, certain machines carried more responsibility than others. Among them were the massive rolling mills used to shape armor plate. At the heart of the operation stood a machine that looked deceptively simple. Two enormous steel cylinders rotated toward each other, separated by a narrow, adjustable gap. Into that gap, heated slabs of steel were fed. Before entering the rollers, the metal passed through furnaces where temperatures exceeded 2,000 degrees Fahrenheit. At that heat, steel glowed orange and red, becoming soft enough to reshape under pressure. Workers guided the slabs carefully toward the rotating cylinders. When the metal entered the rollers, forces far greater than anything visible to the human eye took over. The cylinders gripped the steel, pulled it forward, compressed it, and forced it outward into a thinner, wider plate. Each pass through the rollers changed the material. Thickness decreased, surface structure altered, internal grain aligned to strengthen the finished armor. Often, the steel passed through multiple times, gradually reaching the precise dimensions required for tank hull construction. The process looked controlled, measured, almost slow. But appearances can be misleading. Each roller weighed many tons. Their rotation carried enormous momentum. The pressure exerted on the metal between them was strong enough to permanently reshape thick slabs of steel. Behind the visible motion existed forces measured in hundreds of thousands of pounds. Heat, torque, pressure, and rotational inertia all combined into a single continuous system. To the workers operating nearby, the machine eventually became routine. After weeks or months on the job, the roar of furnaces and the vibration of rollers faded into the background of daily work. Humans adapt quickly to their environment, even extreme environments. But the machines themselves do not adapt. They accumulate. Industrial disaster rarely fail because of a single dramatic mistake. More often, they fail because small changes build over time. In the rolling mill, every slab of heated steel created a cycle of stress inside the rollers themselves. When the glowing metal entered the machine, heat transferred rapidly into the surface of the cylinders. The outer layers expanded slightly under the temperature increase. The interior remained cooler and expanded less. This difference created internal tension. When the steel exited and cooler air contacted the rollers, temperatures dropped again. The surface contracted. The internal structure resisted. Then another slab arrived, and the cycle repeated. Expansion, contraction, expansion, contraction. Thousands of times, over days, weeks, months. To an observer, the rollers appeared unchanged. Their polished surfaces continued turning smoothly. Their dimensions remained constant. But inside the metal, microscopic structural changes slowly accumulated. Tiny imperfections formed along crystal boundaries in the steel. Under repeated stress, these imperfections could grow into microscopic cracks. At first, such cracks were far too small to cause concern. In fact, they were too small to detect with the ultrasonic testing, and advanced non-destructive evaluation methods had not yet become standard industrial tools. Engineers relied mostly on visual inspection and operational performance. If the machine continued functioning normally, it was assumed to be safe. But structural fatigue does not always reveal itself externally. Inside the rotating cylinders, stresses continued building in places no one could see. Wartime production put enormous pressure on factories to maintain constant output. Equipment rarely stopped. Maintenance windows were short. Machines designed for heavy workloads were often pushed beyond what their designers originally anticipated. The rolling mill was no exception. Armor plate orders were high, production schedules were tight, and the machine performed exactly as expected, day after day. Workers developed confidence in it. It became part of the landscape of the factory floor. But the internal crack that had begun forming within the roller did not disappear. It grew, slowly, almost invisibly. Each time the machine rotated, forces traveled through the structure of the steel. Most of those forces were safely distributed, but near the microscopic crack, stress concentrated along the tiny fracture line. Every rotation widened it slightly. Every heating cycle encouraged it to expand deeper into the metal. Eventually, the crack reached a critical length. At that point, the roller still appeared solid. It still rotated. It still compressed steel. But its internal strength had already begun to decline. On the day the machine failed, the factory floor followed its normal rhythm. Workers guided glowing slabs toward the rollers. Steel plates emerged from the machine in long sheets destined for further shaping and machining. Furnaces roared continuously. The environment felt no different from any other production shift. But deep inside the rotating roller, the crack had grown large enough that the remaining structure of the steel could no longer distribute stress safely. For a brief moment, the forces inside the metal reached equilibrium. Then, the equilibrium disappeared. The crack expanded suddenly across the interior of the roller. When it reached a critical size, the remaining cross-section of steel could no longer support the mechanical load. At that instant, the roller fractured. This was not an explosion in the chemical sense. No fuel ignited, no pressure vessel burst. Instead, enormous stored mechanical energy suddenly lost its containment. The rotating cylinder split under internal stress while still moving. Fragments of steel were forced outward by the momentum of the machine. Heavy components broke free from the structure. The sudden imbalance caused the entire system to tear itself apart within seconds. Workers nearby heard a sharp metallic rupture, far louder than the normal sounds of the factory. Then came the violent motion of machinery no longer constrained by its original design. In an environment filled with moving equipment and intense heat, events unfold too quickly for human reaction. Within moments, the rolling line that had been operating continuously was reduced to twisted metal and scattered fragments. When the machine finally stopped moving, the immediate environment had changed dramatically. Steel fragments lay across the floor. Parts of the rolling assembly were bent or broken. Nearby equipment had been damaged by the sudden mechanical release. Workers in the surrounding area quickly shut down other systems to prevent additional hazards. Furnaces were reduced. Conveyors halted. Emergency teams moved into the area. Industrial accidents were not uncommon in heavy manufacturing during the early 20th century, but events involving large structural machines were taken seriously. Engineers began documenting what had happened. Damaged parts were examined. Sections of the fractured roller were removed for inspection. Even without modern testing tools, investigators could see evidence of fatigue where the metal had broken. The fracture surface showed signs that a crack had existed long before the final failure. Events like this gradually influenced how industrial engineers understood machine reliability. At the time, many systems were designed primarily for strength. If a structure could handle the maximum expected load, it was considered adequate. But fatigue failures demonstrated that repeated stress could destroy even very strong components. The concept of fatigue life became more important. Engineers began studying how many cycles of stress a metal component could endure before microscopic cracks might begin forming. Maintenance practices slowly evolved. Periodic replacement of critical components became more common, even when those parts still appeared functional. Inspection methods also improved over time. New technologies eventually allowed engineers to detect hidden cracks before they reached dangerous sizes. Ultrasonic testing, magnetic particle inspection, and other non-destructive methods were gradually introduced into industrial maintenance programs. These developments were not immediate results of a single event, but each incident contributed pieces of information to a growing understanding of how machines behave under long-term stress. Despite occasional failures, the industrial system built during World War II achieved an extraordinary level of output. Factories across the United States produced enormous quantities of military equipment in a remarkably short period. Tank plants, aircraft factories, and shipyards transformed the scale of manufacturing. The Detroit region alone became responsible for producing tens of thousands of armored vehicles during the war. Behind those achievements stood millions of workers and thousands of machines operating continuously under demanding conditions. The incident with the rolling mill became just one small part of that larger story. Production resumed after repairs were completed. New components replaced damaged equipment. The factory continued contributing to the massive logistical efforts supporting Allied forces overseas. But the lessons learned from machine failures gradually shaped future engineering standards. Industrial systems became safer. Maintenance procedures improved. Designers began considering not only how machines operate, but how they age. Large industrial machines rarely fail without warning. The warning simply does not always appear in ways humans can easily notice. Sometimes it exists as microscopic damage hidden beneath the surface of steel. Sometimes it develops slowly over thousands of repeated cycles. And sometimes it grows inside structures that appear perfectly stable from the outside. The rolling mill that failed during wartime production was not poorly built. It was not recklessly operated. It was simply a machine pushed into continuous service during one of the most intense industrial mobilizations in history. Under those conditions, even strong materials can reach their limits. Today, engineers understand much more about fatigue, inspection, and structural monitoring, but the lessons came from decades of real-world experience, often learned in factories where machines revealed their limits under pressure. And occasionally, those lessons began with a quiet change in rhythm inside a machine that no one expected to fail.